So now we're going to talk about AutoML for image data. Unlike the case of tabular data, for image data, it's pretty clear what type of model is the best, a convolutional neural network. In this tutorial, we will demonstrate how to train models for classifying images with AutoGluon. AutoGluon can also be used for object detection in a really similar way. Our tutorial will not dive into the technical details of convolutional neural networks and modern computer vision. For background on this, please study the linked textbook, Dive into Deep Learning, particularly chapters 6, 7, and 13, which provides a very comprehensive and accessible introduction. As for tabular data, AutoGluon will help you easily train models for these vision tasks with just a single call to fit. We begin by specifying image classification as our task of interest and importing AutoGluon. Next, we format our image data set. Here we consider an example image classification task comprised of a subset of the SHOP-E-IET dataset. Each image in this data depicts a clothing item, and the label describes which clothing category the item belongs to. The dataset is really small here just to ensure our tutorial can run reasonably fast for you. Typically, image classification tasks can take quite a while. So here's the command to download this data from our cloud storage bucket and unzip it on your local machine. This will unzip the data and print some basic directory information about the data set, as well as plotting some examples of the data shown here. We can see there's 4 classes: baby pants, woman chiffon top, woman casual shoes, and baby shirt, for which there's 200 images from each class in the training data. Here's what the data would look like on your local directory. There's a training folder that contains the training data with subdirectories containing the class names. Within each subdirectory, we have the 200 images corresponding to that class. Baby pants, in this case, is shown as an example. Likewise, we have test data that corresponds to the same subdirectory structure with here only 20 images per class. You could also have an unlabeled test data set that would just contain only the images without this subdirectory structure based on class names. Let's load these image data into AutoGluon. We do this just similarly as to how we did it for the tabular data sets via task.dataset. Here, when we try and print this training data object, we see that it's an AutoGluon object and it has basically nothing in it. Unlike for tabular data, AutoGluon avoids loading the full image data set into memory because these can grow quite large. We can work with the data set by initializing it, calling init here. Now we can look at some attributes, say the .classes attribute, which will list the class labels and their order, which is important because when we call predict, the predictions will correspond to indices in this list. We can now train an image classification model via a fit call. Here we just train it for a very little amount of time, just 3 epochs. To ensure this tutorial runs quickly, we only run 2 trials, meaning only 2 different networks are trained. And here we specify that there's 1 GPU available to use in each training run. If you don't have a GPU, you have to set this equal to 0, but it will take very long, probably. Convolutional neural nets are really designed for GPU-accelerated hardware. So here's the call to fit. It looks pretty similar to what we had for tabular data. And again, many of these arguments are optional. And here's the output. Let's actually look at the live. Let's actually run this command live to see something more exciting because it will print some dynamic output. So here what we see is that when we called fit, this job scheduler started preparing training of networks on the GPU. Here we see that the scheduler is planning to train 2 different networks because we specified that in this num HPO trials argument here, num trials, sorry. And each of these trials will involve training one network with some particular hyperparameter values, and it will be trained for 3 epochs. Here we see that the first epoch has just completed and the validation accuracy is 0.35. Now the second epoch completed, and so on and so forth. So let's skip ahead and just look at the final output. Looks like this. Within FIT, basically the data set is automatically split into a random disjoint training and validation subsets. Multiple networks are trained under different hyperparameter values. Here there's just 2 of them. And finally, the network with the best hyperparameter configuration is selected based on its performance on the validation set. Here below, we plot the validation accuracy achieved by this network. In the final step of FIT, this best network is refit to the entire data set, merging both training and validation subsets, using the same hyperparameter values to produce the model that will be used for inference. Here's how you can plot the resulting best validation accuracy achieved by any of the networks for the trained classifier. Given a new image, we want to use our trained classifier to predict its label. Here's how to do that. Here we see that this image is classified as baby shirt with confidence 49%. We can also print the predicted probability of each class assigned by the classifier. We see that the classifier thought another plausible class could be woman Schiff on top, which seems reasonable to me. Now we load a test data set of new images and evaluate our classifier over all images in this data. As I showed before, the test data basically has the same subdirectory structure as the training data, and it's super easy to evaluate the accuracy. We just call classifier.evaluate. It will call predict internally and then calculate the resulting accuracy of the predictions. What happened during FIT? Let's print a summary. Again, we can call classifier.fitSummary just like we did in the setting of tabular data. Here we can see that some basic statistics about the model fitting process, such as the number of classes, the best hyperparameter configuration here, the number of resources available for each training trial, etc. Here we can see some information about each training trial corresponding to the training of one network, including the hyperparameter configuration that was used and the resulting accuracy on the validation data, here called the classification reward by the hyperparameter optimizer. As for tabular data, there will be a summary of models plot that we can mouse over and look at some more detailed information about each model saved in this file. And we can also see the best validation performance achieved so far after this many completed training jobs on the x-axis. In this case, we just have 2 training jobs, so it's not a very exciting plot. Let's talk about what actually happened during FIT. First, the data was pre-processed and split into training validation sets. Pre-processing includes resizing and cropping images to ensure they're the right size for our models, as well as normalizing the values at each pixel based on their statistics across the data set. We can optionally apply data augmentation to increase the size of the data set available for training. For example, you can tell AutoGluon to use the simple but effective mix-up augmentation strategy by specifying the fit argument shown here. Mix-up is a really simple trick in which you take 2 images and mix them together, as shown here, to create a new synthetic image whose label is basically just the combination of the 2 images' labels. Another step of FIT is to load a pre-trained convolutional neural network from gluon CV, which is a repository of pre-trained computer vision models that have been trained on a large data set of images, usually the famous ImageNet data set. By starting from a pre-trained network and fine-tuning this network's parameters on our data set, the network can transfer its previously learned knowledge of useful image features like edges, textures, etc., or parts of objects even, to improve what it learns from our labeled data set. This is particularly important if our data set is pretty small, as is the case here, transfer learning enables us to achieve good accuracy with less data than we would otherwise need to provide in order to achieve the same accuracy if training the network from scratch. Of course, you can still disable transfer learning just by setting used pre-trained equals false in fit. Here's sort of what the model zoo looks like in AutoGluon. The available models shown here, their inference latency on the x-axis and their accuracy on the pre-training task shown on the y-axis. Next, we need to suitably set up our network architecture for the particular classification task of interest here. In this case, it was classifying images into one of 4 classes. That typically means that we need to modify the output layer of the pre-trained network, which will have been pre-trained on some other task. So typically what we'll do is we'll chop off the output layer of the network, randomly create a new output layer, in this case an output layer that outputs 4 values corresponding to the predictive probability of each class. We'll randomly initialize that new output layer, but we'll copy the parameters from all of the lower layers from the network trained on the source data or the pre-trained task. Then we will train the output layer from scratch with randomly initialized parameters while simultaneously updating the parameters of all the other layers on our own data set. We will repeatedly train neural networks under different hyperparameter configurations to find the best hyperparameters to use. Each training run of a network might leverage multiple GPUs, and 2 training runs of networks with different hyperparameters might be run in parallel on different sets of GPUs as well. For example, if your machine has 4 GPUs and you specify num GPUs per trial equals 2 in fit, then AutoGluon will at any given time be running 2 training jobs in parallel, each using 2 GPUs. Hyperparameter tuning will be described in more details in the next tutorial. The next step, after we found the best hyperparameter configuration for our network, is to retrain a network under the same hyperparameter configuration for the same number of epochs that were optimal on the previous validation set, but now on the merged data set that contains both the training and validation data, aka the full data set. We can optionally construct a more accurate model ensemble of multiple networks by specifying the fit argument ensemble. Here we use a very simple ensembling strategy that's popular for deep learning in particular, called deep ensembles, in which you just train multiple copies of the same neural network just with different random initializations. And there's also some additional randomness in the training process due to stochastic gradient descent, which operates on random mini batches of data. Because image classifications are much larger and slower than tabular data models, it may often not be preferable to do ensembling, especially sophisticated ensembling like stacking, which is why we just stick with the simple deep ensemble strategy used here. Since the neural network optimization is highly non-convex, even just retraining copies of the same neural network with the same hyperparameters on the same data suffices to create a diverse ensemble. For more, see the following references. In particular, check out this Medium blog post to see some benchmark results when we applied that one-line fit call to various Kaggle competitions involving image classification. Check out the Dive into Deep Learning textbook for more background on computer vision models and especially convolutional neural networks. Check out the gluon CV paper for more information about the pre-trained models that are available and how they were produced. And then check out this Bag of Tricks paper, which describes some tricks you can activate inside AutoGluon that might help you boost accuracy in your image classification tasks.